Hey! I'm just checking if microphone is working. Okay, we seem to be live. Welcome to Automat Live Coding. On this stream we are writing a game that plays other games. It's a set of components that you can assemble that can do stuff on your desktop. They can press keyboard keys and move mouse and click mouse buttons if you arrange them properly. We are in the process of adding mouse support. So those objects, I think they will be refactored a little bit over the time, but I can show you what we have so far. So we have this macro recorder that can record sequences of events. If I position my cursor somewhere here and zoom in, you can see that this is a mouse trace, and it's composed of a lot of very tiny movements. So each dot that you can see here, this vertical blue line, very subtle, barely visible, corresponds to a small movement of the mouse cursor. Together, when I zoom out, it forms this sort of mouse trace. When this is connected to an object that can move mouse, it can do exactly that. When I play it, you can see that the mouse, my hands are here, but the mouse is moving by itself. Most operating systems allow this kind of event injection, so it's possible to programmatically control mouse. This is for accessibility reasons, usually. In our case, it works decently well, but we had some issues. So we have been dealing with some crashes. Every now and then, Automat just crashed. And I was looking into this during the second half of the last stream, and I intend to look into this a little bit more, because crashes in this sort of application, they're basically deal breaker. If I am supposed to leave Automat for a long time operating some game, the point of Automat is to do it. Is for me to not to monitor it constantly. The point of this is to actually take the hassle of managing everything. Like, the reliability should be there. I should not be thinking about whether this tool crashes or not. The point is that this tool should be reliable. So we have to address those crashes. When I was tracking them down, it seems like they point to a uniform buffer allocation issue within Skia. And when I read more about Skia, it turns out that even though it supports multi-threaded recording of commands, it's not entirely optimized towards being multi-threaded. I mean, the way it is used in Chrome or in Chromium is that it actually has two threads. Just two threads that are recording commands, not like in Automat where we can have 12 of them. And we are actually making use of all 12 of them because we have tons of widgets, and each widget is a sequence of commands that has to be recorded. Quite unfortunate. Anyway, so it is possible that Skia, because it has slightly different objectives, it's optimized towards slightly different use case. It's not optimized towards massively parallel PCs, it's optimized towards a little bit of parallelism, where you want to delegate some work to background thread, but still you're not using those insanely multi-core CPUs. Still, I will try to take a look and see if we can solve this. It's possible that we will just reduce the number of threads, or like we will do something with them to fix this. So to address this, we will actually switch to a different machine. I have a Windows machine next to me, So I will have to reconnect some cables and then we'll be able to do that. The Windows machine has another problem. The Windows machine has an Intel GPU, and Intel GPU, when you create Windows on Windows, those Windows textures, I mean the texture that the application renders itself to, it cannot be used as an input attachment for other shaders. So it's not possible on Intel GPUs on Windows to read your window back as a shader. So you cannot, for example, frame to frame, use the previous frame to display the next one. It's something that we are not really using, but for some reason Skia needs it. So we will work around this issue. I started doing this yesterday, and today we are going to finish this. And we will also see if this multi-threading issue happens on Windows as well. I've seen a good way to trigger it was to place a lot of those objects around. A lot of them. Just want to see if we will crash. I should have some sort of object copying mechanism so that I can pollute the world faster. Now, when I zoom in and out, it should cause terrible synchronization issues. Maybe I changed something so the issue doesn't happen. We will try to trigger it anyway. It's okay, let me do some cable management. How are we? Okay. So this is the Windows machine. I can fire up cursor. I'm also using cursor here. I was trying to use the Claude, the AI agent, to help me write this, but it wasn't particularly successful. Okay, I was actually exploring a very particular solution that's probably not going to work. Let me see if I managed to get it to run. It may not seem so, but we are on Windows right now. Yeah. So Skia uses a library called VMA, and Skia configures it in a very particular way, which I cannot reproduce. So there are some differences between them. Actually, I think I just need to pass an array of function pointers when I initialize VMA. So when I do this, I can do p vulkan functions. I could probably just populate this array, I mean this data structure, with function pointers, and I think that should make it work. But I had a different idea. So what is the problem? When we are starting Automat, we are getting a couple of textures from the operating system. The operating system gives them to us and tells us, this is your window, this is where you can render. And we render there. But those textures Skia doesn't like them. Skia wants a texture that has slightly different capabilities, so we have to allocate it ourselves. And once Skia finishes rendering, we have to copy over the stuff that Skia rendered onto the window surface. This is the workaround. The approach that I was trying was to allocate my own texture for Skia and have it rendered there. The problem is that allocating memory on the GPU requires a custom allocator, and Skia already uses the allocator I wanted to use, so there were conflicts. But I think accessing this allocator is kind of like peeking inside Skia, like accessing its internal APIs essentially. And since we are doing this anyway, I can just ask Skia to create a texture for me. It will create the texture that it likes, using the proper parameters that it wants to use. And I will just use whatever Skia created. Oh, we even have this mutable texture state. Oh, wow. Wow, wow. Actually, Skia APIs are kind of nice. It looks like it's very plug and play at the Vulkan layer. I don't want this init VMA anymore. I'm not friends with VMA. I wonder. Actually, maybe I don't need to do anything here. I think those things will be reinitialized by C++ anyway. Okay, so here is the happy path. If the window texture, this is window texture, has this capability, this is called VK image usage input attachment bit. This means that I can use it as a shader thingy. Then I can just use the window surface directly. I can render directly to the window. This is the nicest situation to be in. But sometimes it's not there. And if it's not there, then I have to allocate my own texture. But I will do it differently now. I think I have to check the docs. GPU, VK, yes. I need to use SK surface as render target. I need to pass sk image info. Okay, image info seems to be a rather complex class. I think the best way is to use this, one of those make constructors. Those constructors are meant to help me. Does it have private stuff? It does have private stuff. I really dislike when configuration is done like that, because the best way to pass parameters, complex functions, is to initialize this using this C++20 initialization. Okay, doesn't matter. Should pass dimensions here. What are those dimensions? I will move them up. Color type alpha type. This is a move. Do we have any alpha types here? Is this what we want? move it here. Okay, so here I am choosing one of those modes. I think I can use this in a single place. Maybe I don't need to initialize it. So here are the capabilities of the device. If it supports pre-multiplied alpha, then I will say, hey, I want to use pre-multiplied alpha, then post-multiplied alpha. Pre-multiplied alpha is best because it allows the compositor to avoid some multiplications when compositing our surface. Then post-multiplied, then if there is the inherit bit, then we will enable this, and here we will say pre-multiplied. Okay, there are just 4 possibilities, and we handled all of them. Okay, and there is an assertion that makes sure that one of those is the case. I can probably remove this assertion from here, because we are checking for this. Actually, instead of crashing outright, I will just log this as an error. maybe error once even. And let's assume this is opaque. This is something we are not using, but we will, and it's going to be really, really nice once we implement this. Filters. Okay, let's continue. Now we can specify alpha type, and there was also a way to specify color space, and I think so we make shared pointer to color space. I think we used color space in some places. It's just sRGB. Okay, this image create info is, we don't need it. I should choose everything for us. We don't need this buffer allocate info. Actually, no, we need it. This is for copying stuff between textures. Actually, wonder. Skia defines this backend texture. What can we do with it? Some YUVA. Okay, I think it's better if we have render target. Render target seems more appropriate.
Knight says,
Hey everyone.
Hey, Knight. Maybe I need to create this backend texture after all. Instead of this vkine image, I will actually not have a surface here, we have surfaces here. Here I am going to have oh. Now I need to make sure everything will work with this. should not be... Actually, no. Will be necessary. This deserves a comment for each. Okay, I'm doing this allocate command buffers. Actually, no, we don't need this barrier. This is Vulkan madness. We have to kind of slowly build a graph on the GPU that will perform as sequence of operations. Here, we just allocate this command buffer. Skia will output the texture in the proper layout. Okay, we need to pass this. Let's do it differently. So for each bug buffer, I need to semaphore. Here we are recording commands, boring. Okay, and this backend texture apparently has value semantics. So it should be fairly small, right? Size 224 bytes. Not so small. Okay, and this is the point where I will have to access the implementation details of Skia. If I remember, in Skia src, look for a VK image. Vulkan graphite utils. Exactly. This is what we need. So we are going to include this file. This is, like I said, implementation detail of Skia. But we need it. Graphite backend textures, and we can get this VK image. Honestly, it feels like this. I was looking at other pieces of Skia, and it seems like, for example, Ganesh. Ganesh exposes this. Ganesh backend, you can get VK image out of a texture. Read about this copy image. Okay, let's say we will copy from this. Format. What format? This sounds good. And new layout is going to be this present SRC. This looks decent now. So this is the present function. So if we are rendering off screen, the texture is going to be like this key. So we are telling Skia to finish rendering in a slightly different state. So normally Skia was asked to finish rendering the surface in a state which makes it easy to show the image on screen, to prepare it for presentation, and if we are rendering on screen, we are telling it, hey, we will copy this image now. So if we are rendering off screen, actually, be right back. Okay, just a couple errors and it should. And we will see if it shows anything. This is the thing with Vulkan, you can never really know. Don't need this init VMA. Don't need this error message. More issues. We don't need to clear up this stuff. Okay, what do we have? Validation error. Synchronization 2 was not enabled. Let's see. It's a weird sound. Okay, let's just enable this. It should be somewhere in the initialization. One of those initialization functions should have this. Extensions. Okay, this should be in device init. Probably not here. Maybe here. I wouldn't require this. I think it would be good enough if we just check get extensions. And desired extension. That actually makes more sense. It's not relevant for device selection, the extension presence. It only makes sense later. Yeah, and we have our synchronization. Synchronization 2 must be enabled. Enable extension if present. There's probably some extra setup that we need to do to make it work. For example, initializing the actual device.
Menka says.
Most of the people would have used the AI if they would get stuck in your situation.
Yeah, I did try this yesterday. I was actually hoping that AI will be very good at this because Vulkan tends to produce lots of code and thousands of people around the world have implemented it thousands of times. But it was making stuff up, the usual problem. I can actually try it, but first I will commit whatever I have so that it doesn't mess with my existing changes. It really wants to include this Vulkan core. It's irrelevant, so I can move here. Actually, it can be mixed. It's fine if it's mixed. I will try firing up Claude. Maybe Claude knows how to enable this extension, but this is probably... I'm using a library to manage Vulkan setup called Vulkan Bootstrap, and the chances that it knows the API are very slim. Okay, this looks fine. Yes. Yeah, okay, looks fine. In the meantime, this should be explained in the, about getting stuck. It's not really about getting stuck, it's just I need to find the documentation for this extension. It should have... information of how to set it up. How do I enable this? It doesn't mention any special setup. This. It links correctly, but does it run? It looks like exactly what we wanted. There was a block during device initialization missing. I actually thought this would be mentioned here. Yeah, this is a little bit annoying because the documentation, the Vulkan documentation, doesn't mention that you have to use this structure. You have to stumble upon this. Nice. It's just a boolean, I think. Failed to create Vulkan swap chain, huh? Oh yeah, because the next was probably not chained properly. What? Did I tweak the usage flags? Yes. I forgot the most important line. So if this usage flag is missing, then I need to add it here. Oh. There it is, our window. It's very laggy because we are using validation layers and they are logging a lot of issues. Let's see what they are. Invalid image layout. It's probably my my work here. This layout issue is strange. Present SRC. There are just 3 places where this could happen. On this. Okay, this is one of the costs of using AI agents. They fixed some of the things, but they've also done this. So this should have been transfer DST.
Cyrus says.
What you doing?
Hey. There are so many answers to this question. Right now I'm fighting with Vulkan, but the bigger thing we're trying to do is we are writing a desktop automation app similar to AutoHotkey. Stuff that can, an app that can press mouse buttons and send keyboard keys to other apps. I mean, it works. It's just logging a lot of issues. Let me check. So there are some layout transitions that I'm doing. I'm telling Vulkan to transition memory layout of the window surface from whatever to this, then doing the copy, then making it presentable, then presenting. Of course, there will be more issues. Wow, look at that. All of the issues are gone. And it even doesn't work that slow anymore. Yeah, so this is what Automat is. It's a collection of objects that can be connected together to do all sorts of things. I misclicked it. Again. So this one is going to, every 3 seconds, it's going to press the mouse button. So now it grabbed my window, and now it released it. Oh, sorry for the loudness. Better. Yeah, this is a very basic macro. Presses mouse button periodically and change it to actually do clicks. So this macro immediately disabled itself. And now it should close Automat. I mean, it clicked the close button, but Automat now crashed. But okay, we've done this. So the workaround for Intel devices works. Thinking about cleaning this code a little bit. This VK semaphore, it could be just called VK. Or nothing. Okay, since this is working, could I trigger the same issue, maybe? And build the release variant. The release variant should have more optimizations, and it should be more likely to hit this, because this is, I think, a concurrency issue. It happens only under very narrow conditions, like not too many threads, not too little threads, not too few threads. and optimizations have to be enabled, and then it happens. Switching to our to-dos. Okay, we have validation layers. Okay, Intel workaround is there. Oh, we have to compile Skia, I see. It's going to take a while. But there was one more thing I wanted to do, and that was this. So in the most recent version of Skia, I just updated Skia to the most recent version. This is why it has to reinstall itself. Skia has a new feature called Vulkan Preferred Features. And I don't enable almost any features on my Vulkan context, Vulkan instance, so maybe it would make sense to actually use this class. So one thing we will do is we will have this object. Let's include GPU VK. Not here, here. I'm using global objects anyway, so I will just make it global. In the init function, will be lowercase. Actually, this is where I'm selecting the instance version. Something is wrong here. Why does it show the mouse? It's moving down. This is weird. Let me record another one. Maybe it's because I'm using... Yeah. That seems to have been caused by KVM software that I'm using. So now on this timeline we can see whole sequence of actions. And this used to crash fairly fast. And I also had some issues with shadows here. They were totally messed up. Why it works? Something crashes still. Okay, there will be stuff to debug. There are actually properties called instance version, API version. I think I'm shadowing them here. Yeah. should be using require API version. I'm wondering what's the proper sequence of operations. I have to scan the system for a Vulkan instance that satisfies this. But I don't want to enable extensions yet, because I need to ask Skia. I need to tell Skia what version I found. Device instance builder. It looks like I have very little choice here, actually. So the next thing I should be able to do is this add to instance extensions. this VK Bootstrap, because it doesn't allow me to access its internal APIs, it's making some things harder than they should be.
Meta 45,500,000.
Yeah, this library is annoying. It prevents me from using Skia.
CP Chica says,
Hello?
Hey, it's preventing me from using Skia's ability to dynamically ask for new extensions. Like optionally. It looks like this library doesn't even consider it to be possibility to have some optional extensions. There is system info. Let's do this. Let's check how to query this. Okay, this should work. Yeah.
Any progress on your Vulcan issues?
Actually, the issue is solved. It's solved because now I create a separate texture rendered to my own texture, and my own texture has whatever config I want to have. And then when I present it to screen, I just copy the separate texture to screen. It's not perfect, but it only happens on some GPUs, like my laptop. Right now I'm on my Windows laptop. And there is... Vulkan is kind of strange because I have a very strong love-hate relationship with Vulkan. It becomes sometimes so annoying, but on some level it's also very elegant. for instance, plugging multiple apps into a single Vulkan kind of rendering pipeline. It's just incredible how well it works. Because it has this graph-based structure, you can ask a library to kind of generate its own set of command buffers or whatever, and just give you the resulting images and semaphores, and you can then plug them into your own stuff. It's very nice in this way. But the boilerplate, it's insane. Actually, this should happen here, I think.
We need Vulkan GL with OpenGL like API made directly from Kronos.
And a lot of the Vulkan things would probably be easier if the calling convention was kind of nicer. So what you usually have is, in many functions, you have to pass this massive struct with configuration, but sometimes you pass some function arguments to the function, and sometimes you pass some of them through fields of this struct. It's probably for efficiency, right? But if they kept to this struct model, and in C++20 there is this way to pass parameters where you can have struct params, and you can have a function with which looks like that. And the only way to call this function is to construct a local params like that. So it will gladly take this syntax. And it's super convenient, because if you miss any arguments, those missing arguments are initialized to zeros, always, in this syntax. And it doesn't force you to... It reduces the size of the code quite significantly if you do it like that. Just the API is more convenient to use. And there is also a lot of situations where you have arrays here, right? So you can have something like that. It's also possible to solve this something like span. I don't think std span would work here, but it's possible to create a custom span that will take initializer lists, so that I can have something like this. It's complaining because I cannot use initializer list, but this is just about initializer lists are constant variables in memory, so I would just have to create my own custom class here that would take initializer lists.
Worst case compiler yells at like it always does.
No. Worst case, you don't learn about the issue until you enable validation layers and you have the same setup. It's about locality of code. Issues are much easier to see if all the code is in the same place. If the code is scattered over multiple files, multiple modules, or even multiple lines, in the case of Vulkan API, it's harder to spot issues. So a proper C++ API would help quite a bit. But a proper C++ API is non-standard and it's confusing. It has to be done by Kronos. If Kronos doesn't do this, then any independent implementation is just going to make it worse. This is private, of course. Why is this private?
Why is there private modifier in struct?
Just to annoy us. There is a way around this. This is... This is it. And it solves many issues. I could do this before including this file, and that would actually make it work. But I'm not going to do this. I would go to programmer jail if I did it.
Was about to say define private public moment.
Okay, anyway, so we are now enabling those instance extensions. I actually wonder what those are. So
Define true rantanen is jail. Define private public is appropriate in some cases.
Yeah, I can see that. The whole reason we have this private public thingy is because C++ came out in 90s, where there was a big craze about encapsulation. People were saying that encapsulation is the key to, to engineering huge systems. That, it was kind of like, I guess, I was too young to remember that time, but I guess it was a little bit like AI craze today. Yeah, and some silly ideas are now encoded in our technologies as foundational. So the way to handle private members should really be just like Python is doing this. Just append underscore, and that's enough. Oh, it's a subtle hint that you shouldn't touch this. But you can still touch it if you want. Or the way that JavaScript does it. Or this private implementation pattern, which makes it really tricky to access. But still possible.
Dollar vanilla, man.
Speaking of dollar, I think C++ included dollar in the character set. So I think now it should be possible to do stuff like that. This is a fairly recent addition, this dollar. Dollar and a couple of more characters now can be used. Yeah, I'm waiting for somebody to find some use case for this new character.
Marking fields as private.
But dollar doesn't really have this history. Dollar was just used by some old programming languages as a variable specifier. That was just a generic prefix for variable.
Old weary wave Broadway.
Do you know what would be nice? This dollar name can be combined with custom suffixes. So I can have it doesn't want me to let no literal will invoke this operator. I could probably put some pragma here to allow me to do it.
Remember, key basic and string type specifier.
I want to see what features Skia uses that I didn't have enabled before. No, no features actually. I want to see the implementation of this class. Okay, the whole init. Okay, Skia does not take advantage of any instance extensions. Cool. Sampler filter min-max. Do we use app features anywhere? Let's keep this. This is fine. Skia doesn't use instance extensions. Time to do the physical device ones. Okay, physical device has two lists of extensions. So are those two vectors. This library is slightly annoying. Okay, this is the least I'm interested in. It's being thrown away, of course. Even the naming is messed up. So an object of type physical device contains a variable of type vk physical device called physical device. And how do you call this? Like, it's like 4 levels of physical device. This is Java madness. The good thing is that this is at least included in the namespace. But the better name for this would be VK, something like that. A name highlights what's different about this variable from everything else. This is, like, naming is hard, but this is a very basic principle that's being broken here. So I need to pass this into app features. It's here. this may not be required anymore. It's an empty features object. So all of those extensions that I'm setting here, actually just a couple of them, I have been enabling them only because I think Skia wants them. I don't know what I'm doing, I think. So... Okay, so this is the query. Okay, this looks reasonable. Blend operation advanced seems to be queried by Skia. Synchronization too as well. Okay, I will bring back those extensions. I just want it to start. It will crash, that's fine. I just want to see if Skia is actually enabling anything. Because from looking at this code, it didn't seem so. So this line. I'm not seeing anything here.
F1 freezes Windows terminal for some reason. I've just learned that while compiling Gen 2 kernel for USSL,
Interesting. It's like Control S in Linux. And this is weird, because when I put it here, I think it worked. Yeah, it says there are plenty of extensions here. Physical device init, but in device init, not so much. Okay, maybe this library came up with some funny constructors. No. Okay, it had some value, and then suddenly no value. What's up with that? Maybe like that. I don't know why this would be set to 0. At what point? So annoying. So this struct contains a copy of a physical device. Which I guess it's only set when it's initialized. I shouldn't have used inheritance, it's causing so many issues. Okay, so Skia is very very conservative. It's asking just for 2 extra extensions, load store op and conservative rasterization. Be right back. So if I correctly understand this, Skia just marks those things as enabled. I mean, asks us to enable them. And that's it. It stops there. If I disable sync 2, will Skia enable this for me? So if I understand correctly, this flag there is some flags here. Okay, so there are two places where this can be enabled, either in these Vulkan 13 features or in a separate field. And I think when I'm doing this, Skia is probably enabling some of the features in the base array, which is kind of cool.
I got cable shortage in my home office.
It's not that bad. It's easier to get cables you don't have than to manage an excess of cables. Cables have this annoying property that there are very few ways to categorize cables. The whole idea of cable is to connect two different things together.
I need to find 3M HDMI cable so I can hook up my second monitor. Standing desk moment. You thought it was long enough. Well, desk said, nope. Now it's always too short.
So we have this physical device features tool.
Okay, I changed the old HDMI cable with cable that came with new monitor, and now I don't have burning spots on my old monitor. So I guess monitor panel don't burn and rather cables burning.
seems like calling this add features to query.
Too bad we can't screenshot burnt in spots.
I mean, with a phone you can, right? You can have software burn-in, right? I'm sure it's possible to write an app like that. That would make screenshots and slowly adjust your display. Add features to query. It's a very strange side effect.
Ooh, I just remembered old desktop screenshot prank.
Yeah, there were so many hacks. Changing icons or renaming folders to empty name. That also worked nice. God mode shortcut button. Oh yeah, here are the mystery values. So was key added 53, 51, which is this, and 49. I'm not sure why I have this feature. I don't think I use it anywhere. what will happen if I disable this blend operation advanced?
Low pass effect. Low pass effect.
Hey, it's not available on my laptop. But Skia should be adding it itself. Yeah. Oh, there's a lot of documentation here. It's private documentation, but still. Okay, this is for faster lookup. So apparently those extensions are controversial because they are disabled by default. I could enable them by adding them manually to the list of extensions. Yeah, the Vulkan extension logic is a mess. Could have been, I don't know, just some bit fields. But organized differently. It's crazy that the version moves from one struct to another in different Vulkan versions. This is appending to the list. So now, stuff that we should do is move these extensions init later on. Oh, actually, this is interesting. So, I guess I was telling Skia that all of the potential extensions are enabled. Somehow it still works, but I'm not sure. I'm trying to simplify this code by removing the stuff from those classes and moving it into functions. The less state, the better. I'm not sure if I need this part, for instance. It's so weird that in this library you mark extensions to enable in a physical device object. So weird. And it's so weird that it only returns 2 extensions. Maybe it's because it's already covered by features. Yeah, there is this pnext chain. So most of those extensions, I guess, are covered by features, and only a couple of them have to be enabled through this system. I guess it's fine. It's robust buffer access. Maybe it's good to have it. I should have added more comments there. It works without it, so I'm not going to complicate this. And I think this is why on Linux we had issues. Because I told Skia that basically all extensions are enabled, everything. Yeah. This hurts so much. Why is it using strings? All of those extension names will be in static memory anyway. It can just use car pointers. Okay, I think this is it. We enabled these preferred features. I actually have no idea what features it is enabling. It's just some of those features are added for us. The way that this class, this Kia class, manages features and extensions, it's actually very nice. I just wish this library of VK Bootstrap that I'm using was more compatible. Okay, the change looks reasonable. Okay, that stuff seems to work on Windows. Now I would like to switch back to Linux and see if it still works there. This was synchronized. I should be able to close this, maybe. Okay, some cable manipulation is necessary. I will do it like that. Backend texture, probably. This is the issue here. I guess I just needed a constructor. So I think all of those rendering glitches that we've seen so far were caused by me telling Skia that it has all of the extensions in the world available. Yeah, it looks better now. Will it? It did crash. Okay, it's still crashing. There are no visual glitches, it's just still failing. Okay, let's see how to trigger the crash. I just triggered it just now by scrolling to the center, zooming and doing this for a little while. Okay, so this doesn't crash, but when I start zooming, it still doesn't crash. The new version of Skia messed up text a little bit. The letter spacing is broken. That's what I don't like. This crash seems to happen. Sometimes it happens immediately. Oh, that was a nice one. Just doing random things sometimes causes a crash. This is not a very good starting point. Seems this is everything we have. Oh, I think now we had a completely different issue. I have been recreating the swap chain. And I think this recreation has caused some issue. It's not bad to have of those cables around. Debug mode fixes everything. This is the worst. Okay, it happened. It was just zooming in and out while scrolling. And the crash happened on a different thread now, on the render thread. This is nice. This is so nice because this is the thread where our code runs. So it could be a better indicator of what's wrong. We're just calling abort because the rectangle type is very simple type. Okay, I guess isValid checks whether up and down are properly sorted. So maybe left and right look good. Top and bottom also look good. This crash doesn't make any sense. Okay, I have to check the isValid function in Skia.
Have you defeated final boss of GPS?
I'm still fighting, but I will defeat it. I mean, it will stop crashing eventually. I wonder what happened in this is valid. I can call this. So this is LLVB. Okay, it returns false. But what is the reason? Oh, okay. So radius has to be less than the dimensions of this. We can fix this. The possibility that this was the issue is very slim, but maybe. So essentially when I unzoomed, it crashed. Unzooming was the trigger. Now I can unzoom, it doesn't crash. Maybe that was it. I'm on release build now. Nothing seems to crash. It's very hard to trigger this issue. Maybe that was it. Now when the display gets small, it's rounded like that. Okay, I think that crash was fixed. It was about radius of rectangles. Actually, in Make Simple, I will add a check. It makes a lot of sense. It was just about unzooming. The number of threads probably had nothing to do with it. I mean, that was just one crash. There is probably more. I want to see if this was causing the problem. So release mode. And even when I unzoom, this unzooming may not crash it. At least not consistently. I just reverted the fix and it's still not crashing. Okay, so I don't think that was the fix. Let's see if at least I can log the error properly. Yep.
Low pass effect.
Okay, I think we will see this error again. I just need to find a better way to trigger it.
I have two options now that I am done with work. Switch my build system from Kamake to Rumpy, or finish drawing a triangle dome.
It's fun that when you do stuff in Vulkan, your achievement is a triangle, but when you're doing ray tracing, which is supposed to be harder, and which you can actually do in like 100 lines. You actually get some nice photorealistic image with reflections and global illumination. Okay, so we won with Intel GPUs. That part works. I think Automat still has this crash, this concurrency issue. I mean, I don't think the issue is entirely in Automat. I think there's probably some edge case about uniforms that Skia is. There's probably some inconsistency in how Skia tracks uniforms when there are multiple concurrent recorders. And it looked like some lifetime issue, because it was crashing when it was deallocating some pointer. Which is the worst to debug. Okay, I will grab some food, and I actually had some videos to watch related to Better Software Conference, so maybe we can check them in a moment. So we've been watching the conference like a week ago. We've been watching some talks, like we watched the talk by Casey recently, and some of those other talks, they also seem kind of valuable to us, like real-time debugger visualization. This is kind of what we are doing with our assembly. We have a real-time debugger. Automat is a real-time debugger. We are not using the standard debugging facilities. We're doing stuff slightly differently because we're using signals to get registers. We're actually not attaching ourselves as a bit tracer to another thread. But that would be interesting. I guess all of them would be interesting. This parallelizing physics solver, I mean, when I look at this thumbnail, I can see something that looks like Tracy, so that makes me curious how it works. So, in a minute, we're going to watch this.
All right, welcome back.
But in a minute. Okay, cranking the volume up. That conference was recorded with very low volume, but maybe they fixed it in post, so let's start slowly.
Back everyone, and thank you Casey for the previous talk. Amazing detail and amazing amount of research you must have done on that. This talk is hopefully going to be a little bit shorter, so we get lunch. So Sam reached out to me a couple of weeks ago and asked if I wanted to present something, and I came to think about this work I did about half a year ago on optimizing and parallelizing the constraint solver for our upcoming game. And as it turned out, this talk isn't going to be that much about the constraint solver or how to parallelize it. It actually is going to be more about the low latency thread pools and
yeah, which is even more interesting than actual physics solver. Low-level thread pools is you need it to nicely distribute work. I wonder how does his experience compare to how Automat does those things. Let's see.
Job system that I had to write to make it all run efficiently on modern hardware. So, but I hope you'll enjoy it anyway. You're going to see some physics movies at least. So just some background on me. I'm Dennis Gustafsson, and I am the original creator of the game Teardown, which is a voxel sandbox heist game that came out in 2020. I was also the only programmer on the project up until the initial release, and now we're a bit more. It features a custom software voxel ray tracing engine, which is pretty special, and also a custom physics engine that operates and does collision detection directly on voxel volumes, and a bunch of other stuff. If you haven't played it, ask me afterwards. I have a bunch of codes to give out if you want to try. So for the last year and a half, I haven't actually been involved in the further development of Teardown, even though the development continues. I've been making prototypes and started to implement a new engine for our an upcoming game, and that's the one I'm gonna talk about today. So it's an engine that is relatively similar to Teardown. We wanted to take all the things we learned from Teardown and remove a lot of limitations and restrictions on the old engine, and see how far we can push it, basically. So one of the things we did was to we rewrote the graphics to use parts of the hardware ray tracing pipeline. It's still tracing voxels at the very lowest end. But by doing that, we could up the number of dynamic objects dramatically, because the old engine worked in conjunction with the CPU and the GPU, because I was using OpenGL at the time, because I didn't know better. So I didn't have access to the hardware ray tracing, but now that we do it in Vulkan. I also had to rewrite the physics to feed this new graphics engine with lots more objects. And doing that, most of the work went into making everything run very parallel, because in this time that passed since the development of Teardown, desktop PCs and gaming PCs got a lot more threads. So that's really the key to getting more performance. So a little background on physics engines, even though it's not really the topic of this talk, could be good to know an overview at least of how they work. So you have a bunch of objects, and what you typically do is split the workload up into two phases. So you have first phase is collision detection, which means you're gonna look for pairs of objects that are close or overlapping and figure out some kind of contact points where they collide. And that part is ridiculously parallel. It has no data dependency. You can just split up all the pairs and do them parallel. There are no locks or anything you need to do that. So very easy. The other part, when you have this list of constraints, is the constraint solver, and that takes the dynamic state, which is the velocity and angular velocity of all the bodies, And it tries to advance time into the next dynamic state for each body while taking all these constraints into consideration. And the way Teardown does that in almost every game out there right now is to do that using a method called projected Gauss-Seidel or sequential impulse. That was also another name for the same thing. And the way it works is very simple, actually. You just sequentially satisfy all these constraints. It's like a relaxation method. So you satisfy the first one, compute an impulse applied to body A and B, and then you progress to the next one and do the same thing, which applies impulse to B and C, and then the third one and the fourth one. And as you can imagine, this has to be done in sequence, and that's what makes it absolutely terrible to parallelize, because you have to do the first, you have to complete the first thing before you can progress to the next, because you want the result from the impulse up here to be applied to B before you measure how much of an impulse you want to apply on the second contact. And that makes a huge difference in terms of convergence for the solver if you do it that way. So you go through all these, and as you can imagine, when you solve the first one, it's going to be solved perfectly, but already when you solve the second one, it's going to like disturb the solution on the first one. So now it's not going to be satisfied anymore. So when you're done all the contacts, you're going to have to go back and do it one more time, and then one more time, and one more time. And you do it like iteratively. And a typical number that games use is like 4, 5, 6, 7, 8 times in that range. Teardown uses 8. This new engine uses 6. And yeah, intuitively very hard to parallelize because of this sequential thing. So what Teardown does, and also most other games or physics engines, is to, instead of trying to split the way we solve constraints, is to split objects in the world. So if we have a bunch of objects over there and a bunch of objects here and they don't touch, those can be solved as separate simulation islands on multiple threads. And finding those groups is also relatively cheap. I included a little screenshot here of what it might look like, and also a profiling graph down here. We're going to be looking at these quite a lot throughout the talk. So if you haven't seen them, it's like a frame profiler or like a timeline profiler. Time moves from left to right. Up here you see the main thread, what it's doing in a hierarchical way. And down here I included, these are the worker threads. So it's using a thread pool. Workers are told by the main thread to start high-level jobs, and then all the threads, when they're occupied, they show in green, and when they're waiting for something, they show in black. So each line here should be thought of as a worker thread, and then it also, time progresses, this thread here does something here, then it waits a little bit, and then it works, and then it waits, and it works, and it's all told by the main thread when to do that. And if we look at how it would be split up, we can just intuitively see these simulation islands here. They would all generate tasks that go into the job system. And as long as we have enough of these islands and they're roughly the same size, this is a pretty good way to do it. But unfortunately, in Teardown and quite a lot of games, it looks more like this. You have maybe some small islands here, but if the player is given the chance and a lot of tools, they will do that. And that's going to be one single island, and it's going to take a long, long time to solve that on one single thread, while the rest of the machine is basically doing nothing.
Actually, parallelizing this solver, a couple of days ago, I've seen this atomic float feature in C++. I had no idea where it could be useful. Possibly into something like this, because multiple threads could theoretically atomically increment the same float value. Like, not the same float value, but I mean, a shared vector, for example, two-dimensional vector encoded as pair of floats could be atomically incremented by multiple threads. It's a nice feature that C++ got. I actually wonder how it's implemented in machine code, because I haven't seen an instruction that would do this.
Except for waiting on that. So this has been ever since initial release of Teardown, this has been the biggest bottleneck for the game. And this is a common problem, not just for Teardown, but for any physics engine. So another guy who thought about this a lot is Aaron Cato, author of Box2D, who most of you probably already are familiar with. He worked on this problem last year and released his findings in Box2D version 3 that came out a bit more than a year ago. And he also wrote about this on his blog. And Aaron is a really smart guy and really nice guy, so I just want to give him the credit for this. I'm just using the same thing. So if you want to look up the details, look at his blog. It's amazing. And I just want to quickly describe how it works. It's a technique called graph coloring, and it's a way to split up these large islands into chunks that can be solved in parallel. And it's also a very intuitive method. You go over all the contact points, and you sweep over all of them, and you mark the ones that actually can be solved in parallel. And in order to be solved in parallel, they cannot affect the same bodies. But there's going to be a lot of constraints that affect different bodies, totally separate ones. And in this case, we can just see that these three affect different pairs of bodies. That means we can solve them in any order, or we can solve them even in parallel, and it's going to be exactly the same result. And when we're done, we won't have covered all the contexts. We cannot include this one, for instance, because it's already being operated on by the other blue ones over here. If we just tried to solve all of them at the same time, we would, since they operate on the same bodies, we would have a lot of data races. And would also be, even though we might get some result from that, it also it wouldn't be the same, it wouldn't be deterministic, it wouldn't be the same every time we run it, which is also a property that we want. So when we do that, we have those three, then we have 4 remaining points. What we do is to sweep over those 4, not considering the other that's already solved, and then we find, mark the ones that can be solved in parallel. Note that those red ones, they cannot be solved in parallel with the blue ones. We have to finish all the blue ones first, and then we can start on the red ones. And then we just do that over and over until we covered all the constraints. This is a very simplified case, of course. In a real scenario with maybe thousands of bodies and tens of thousands of constraints, that's going to be a pretty large number of constraints that goes into each color.
So depending on the number of colors, graph coloring is either pretty trivial. I mean, with 2 colors, you can do it with DFS. If I remember correctly, there is still an algorithm for 3 coloring, but 4 coloring is suddenly super hard, super difficult. There are those greedy approaches that find some coloring. They are not necessarily always finding the best one. Sometimes, if you follow this greedy approach, you will end up with 10 colors, where in reality you could just have 4.
And a typical number for that could be maybe 10, 11, 12 colors that's needed to cover almost all constraints. And usually there's a small remainder. We don't want too many colors. So if we have a very small number of colors left, we can just put them in a special bin and go over them sequentially. That's going to be, as we'll see later, faster than making a separate color for each. So we have that. And then when these are fed, when we're going to solve these and we're going to process these after splitting them up, we start with the first color, throw that at the thread pool, and solve all those constraints as parallel as we can. And then we're going to proceed to the next one. And then we do that 6 times because we wanted to do 6 iterations. And in between each color, when these threads have been working on it, before we can start the next one, we have to wait for all the threads to finish. So that's a full barrier sync across all the threads in the thread pool. And we're going to have to do that between every color in every iteration. And as I mentioned, the number of colors are usually 10, 11, 12. And then we have a few additional jobs every iteration for integration and other things. So we end up with close to or around 100 barriers per step, or per time that we execute the solver. And given that this is a game that wants to update at 60 frames per second, and we also have other things to do, we have a collision detection and rendering and whatnot, that gives us just a few milliseconds to complete that. And doing this amount of synchronization in such short amount of time is something that synchronization primitives aren't very good at. So in order to measure how they perform, I put together this little test scene. It's a level exported from Teardown to the new engine. I spawned a lot of dynamic objects, and it's actually 5,000 of them. I made so that they are all active and simulated at all times. And they're all, or most of them, are in a big pile. So it's a tricky case for the physics engine to handle. And the machine I'm running this on is an Intel Core i9, 14th generation Raptor Lake 900F. I'm not sure what those numbers really mean, but it has 8 P cores, or performance cores.
Top of the line
with
CPU.
hyperthreading, so 2 threads per core, and 16 efficiency cores, summing up to a total of 32 threads. Now, whether we should count the hyperthreads or not, it could be discussed, but there are actually 24 actual cores in the machine. And as a baseline, if we run this single-threadedly, we get the number here, 82 milliseconds for the whole scene update, which is obviously not anywhere near real time. But the number we're going to look at throughout the presentation is actually 1 iteration of the solver, marked here. So the thing that we do 6 times, I take an average of that, and that's the number I look at, because that's the thing we're trying to parallelize, so it makes sense to measure only that, right? And if I start out with a traditional, or what I call a traditional thread pool, it's actually very close to the implementation that runs in the current Teardown, or Teardown the game as it is today. It uses just standard synchronization primitives. So it has a shared task queue that fills up every time there's a job coming in. There are multiple workers pulling jobs from this task queue using a standard mutex. And then there are a couple of condition variables. One for if it happens so that the main thread has to wait for the threads to finish. The main thread also pulls tasks off the queue, but sometimes it finishes There's no more tasks to take, but it has to wait for the threads to finish. It sleeps on this condition variable. And the same thing when the workers run out of work, and there's no more tasks to be done, they sleep on another condition until the main thread says, here's a new job. Then they can start again. And it looks like this. And you can already see this is kind of what this looks a bit weird, right? We have very dense profile on the left and a very sparse on the right. And this kind of coincides with what we said before, collision detection on the left, very easy to parallelize, no data dependencies. Solver on the right, very hard to parallelize, and lots of synchronization. So if we just measure the time there, we're at 17 times better than the single thread performance on the collision detection, which is really good, I would say, given that we have, I don't know how much you know about performance and efficiency cores. I'm not a hardware person, so I'm not the one to tell you exactly how it works. But the efficiency cores, from what I've come to understand, there are 4 cores in a cluster, they share an L2 cache, and they also have a clock speed that is lower than the performance core. And that in total makes them run at roughly half the speed of the performance core, from what I come to understand. And since we have 16 of them and 8 performance cores, we should get around 16, and 17 is, so that must be pretty good, right? If we look at the solver,
better than theoretical maximum. So at this point it becomes suspiciously good. But yeah, he probably underestimated those efficiency cores. They're probably not as slow.
We're at 1.4. That is like objectively terrible for having 31 threads on a problem. So I reran this with different numbers of threads just to see what happens. And what's going on, it's a little bit hard to explain, but if I run at 8 threads, I should have had the graph. I didn't actually do all the numbers because it's a lot of manual work. But I tried it, and the one that runs fastest is the one with 8 threads. Now we can observe something interesting here, and that's the collision detection, which parallelizes really well. It sits at 7.6x, the single thread performance, expected because it's very close to the theoretical maximum of 8. Whereas the solver, which was with 31 threads, was at 1.4, is now at 4.7. So one part of the code is slower, another part of code is faster. That's kind of hard to work with, right? So in total, if we just look at the scene update, which is 20.5 in this one, it's 13.3 in this one. So in total, measuring the whole frame time, this one is actually faster. It's faster to run just 8 threads than 31. And the reason I chose 31, maybe I should mention, is that when you have a high thread count like this, I usually leave 1 for the operating system and background tasks. I found that to be good practice, just so you don't get hiccups. But anyway, how should we tackle this? Should we just, and why is it 8? 8, I think, is because we have 8 performance cores. That would make sense. But what should we do about it? And if we go back and look at this one and zoom in on one iteration, that should be able to give us some hints. And then we can notice 2 things. One is that in between, so these are the different high-level jobs, these like vertical green fuzzy bars. In between these jobs, there's a lot of just black space where none of the threads are doing anything. Also not the main thread. which is kind of weird because the whole computer is just sitting there for almost 100 microseconds doing nothing. And the other thing we can observe is that even when a worker thread is running, it's a lot of gaps in between actually processing tasks. And that's likely because there's a lot of contention. We have a single shared task queue and a lot of workers trying to pull from the same queue. So we're going to have a contention from all the threads trying to access the same resource. So I want us to think about these two things as two separate problems, even though they're probably related. To try and alleviate this, I rewrote the job system from using standard synchronization primitives to using mostly lockless programming and atomics. I don't know, how many in here have used or are familiar with lockless programming? So that's more than half. Great. It's a way to spin on atomic variables to wait for something instead of using like an operating system primitive. The operating system primitives actually also use that a little bit. They spin a little bit in user space, usually before actually doing task switch and going into kernel. But that's true for mutex, but from what I come to understand, that is not true for a condition variable. So, and it's also hard to know exactly because it's not really exposed what they do. So we have an atomic spin lock that spins waiting. So when there is congestion pulling these tasks, the atomic spin lock will just sit there and go, is it available, is it available, is it available, until it becomes available, and then it's immediately going to return. So there won't ever be a task switch or like the operating system blocking that thread.
The operating system is what's messing up this. When an operating system sees that you are blocked on the mutex, which is held by another thread, the OS will handle the control off to the other thread, to some other thread.
Or anything. We also have an atomic counter for completed tasks, so that if the main thread is the first one to finish, it's not going to sleep on a condition variable anymore. It's also going to sleep on this atomic, waiting for the number of completed tasks to be all the tasks. And in this version, I still have the condition variable for the workers, because we don't want to spin all the threads in the machine forever, because that's going to consume a lot of energy. The computer is going to be very loud. It's going to be very warm.
Yeah, you don't want to play those games on laptops.
It's a nice thing to do towards other programs. We might get punished by the Windows scheduler for doing that. So we
actually quite the opposite.
Overuse
The scheduler,
this opportunity to spin too much.
when it sees that a thread is very busy, it tends to give this thread the opportunity to run. The threads which are penalized is threads which are inactive and they start from time to time. The CPU also changes frequency, it down throttles. So when there is nothing running and then you suddenly start running, for some time you will run at lower frequency and then the CPU will speed up at some point.
But let's look at what this looks like. So on the left side, collision detection is roughly the same. I think that is within the error margin. Service is probably the same, which is expected. It was already fast before. It's not going to be magically much faster if it's already efficient. And the parallel solve on the right side is now at 3.8 times faster than single-threaded. So we're a bit closer to the 8-thread version. Not quite as good as the 8-thread version with the previous one, but much better than the 1.4 that we had before. And if we look at the scene update 10, that's actually faster. So by using lockless, we could make the whole frame time now running faster with 31 threads as compared to 8 threads that we had before. So by using, we actually get a benefit from using the whole machine, so to say. And if we then zoom in again, it now looks like this. And it's worth mentioning here that this distance here is now 880 microseconds, whereas in the previous slide, it was 2,200 microseconds. So even though it looks like it's approximately the same black gap in between jobs, it's actually much faster because it just scaled up. But we can see that once the threads actually start working on something, they're actually quite efficient. They're almost not noticeable, these little black things where they try to get the next tasks. So we solved one problem, and we made one problem better, but it still looks like something is a little bit off. They're doing more waiting than working still. And I think the solution here is probably obvious to everyone, since we still have that last condition variable in there that we don't want to remove, because the computer, we don't want to waste, or waste all that energy having it spinning all the time. What we could do is to have like two versions of the thread pool. One that spins indefinitely, even when the job is finished, you can just spin from here to there. But we just want to do that while we're in the solver, because we know in the solver that when we finish the job here, all the threads will hang on that condition variable. And then on the main thread, 5 microseconds later, it's going to say, okay, time to wake up, everyone. So then it kind of make this switch, like go to sleep, wake up, go to sleep, wake up, which is very inefficient. But before we look at that, I just want to make mention an observation that I made. And I'm not a hardware person, so I'm not, I don't know what I'm talking about on this one, but I just want to mention it because I couldn't unsee it once I saw it. When I've been staring at these graphs, I see that it's usually when the main thread says start working, there are a number of threads that start early, and then there are kind of a gradual period before everyone started. And the time it takes from the main thread says start until all of them started is roughly like 30 milliseconds or 30 microseconds. And if we just look at these that start early, you can see that it's 1, 2, 3, 4, 5, 6, 7. These are a little hard to measure because they're so small. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You start to see a pattern. It's like almost always it's 7 threads that start early, and then the rest come way later. And my theory is that those are the performance cores, and that's also why the 8-core version is faster. I cannot really back this up, but that's just my theory. But now let's try to remove that last condition variable. So the only modification I made was to have a Boolean on the whole thread pool that basically says if we are in this elevated performance mode or low latency mode or spin mode, as I call it. If we are, we just spin on an atomic while waiting for the next job, or that Boolean to go to the normal state, then we also break that spin. And looking at the results, we're now up to 9.1x on the solver side. Collision detection also went a little bit better, up to 19, but I think that could be, it could also be just random noise, I'm not sure. And overall, we're down to 6.6 milliseconds for the whole simulation time, from 82 So I don't know what that would be. It's like a total of maybe 12, 13.
It's acceptable. But the slide where he showed the
if we
original
zoom in,
80 milliseconds,
as we always
actually
do,
the discovery,
on
the
one
broad
iteration,
phase took most
we
of the
can now
time
see
there.
that this is starting to look pretty reasonable. It's actually doing what it's told. So if the main thread says, can you start this batch? All the threads are pretty quick. They start at roughly the same time. Also, another reminder that this is, again, scaled up, just so you can see it better. It's now 330 microseconds across. So the time it takes to start all the threads here, it went from 30 microseconds in the previous one down to just, you can't really see the legend here, but it's approximately 2 microseconds in this version. And
Nice.
once the last worker stops working, the main thread immediately continues without sleeping and starts the next one. And then it just goes in sync with the workers. The only real gap we have is this one. But that's the serial part. That's the special bin of constraints that didn't get colored that we solve in sequence. It's been there in all the graphs, but it's been so small that we didn't see it. And now we can finally see it. So I see that as a good thing. now the whole graph finally makes sense. So as I mentioned a couple of times now, the scale of this is different in all the slides. And I thought it would be interesting to just lay them out and see them side by side. So I just scaled the image actually to have the same time, so to speak. And now it gets pretty obvious. It's the same amount of, or should be the same amount of green in all these graphs. It's just the amount of black gaps where the threads are waiting that's different. So that's that. And I also actually put them in a diagram like this, where I grouped them a little differently. I have the single-threaded on the left. I did these 3 methods, the synchronization primitives, the lockless or partially lockless in the blue, and then this spinning mode lockless on the right. And then I measured the whole things with 8 threads and with 31 threads to compare. And as we can see with the sync primitives, much faster with 8 threads. With the lockless, still faster with 8 threads, but it's like at least approaching the same range. And if we just spin in between jobs, the 31 threads outperforms the 8 thread one by quite far. This, by the way, is just for the solver. If we would have included the collision detection also, that would be an even more dramatic difference because of the collision detection. I redid the same thing with AMD. I have a Ryzen 7 laptop that has 8 Zen 4 cores, and it uses AMD's version of hyperthreading called simultaneous multithreading. It's basically the same thing. So 16 hardware threads. So instead of 31, I'm using 15 threads on the right side. And I thought it was quite interesting that the overall trend here, or the overall how they differentiate, is roughly the same, even though it's a completely different architecture. So with the sync primitives, 8 is faster than 15. With lockless, about the same. And with green, we do get a benefit from using also the hyperthreads, or these SMT threads. I do have a couple more slides, if we have time. Just some closing notes on having access to a low latency thread pool like this has affected the way I think about parallel programming a little bit, which I thought would be interesting to share at a conference like this. When you have regular task systems or job systems, thread pools, whatever you call them, the most common way to interface with that, to my knowledge, is to have some kind of task that you define. And it could look, if you use C++, it could be like a base class, a task, and then you override a run function, a run method, and then some state that this task operates on. If you use C, it could be a function pointer and a struct. It could look a little differently. And then at some place in the code, you would build a task graph. So you would assemble these tasks. You would allocate memory for them, put them somewhere, copy the state, add them to the scheduler, insert these barriers, and sometimes you have dependencies between the tasks instead of manually setting the barriers, and then all that happens implicitly. And then once you built that, you execute the whole thing, and then that runs, and then implicitly it just calls all these callbacks in the right order from different threads, and just magically it resolves this graph. I never, ever liked this style of programming.
Is that not like Vulkan?
I think it's very different from how I normally think about programming. If I sit down and write like a prototype for something, I would never dream of using this paradigm for doing it. I would just write it like from top to bottom, like sequential code. And usually this is necessary because you want these dependencies kind of stated in that graph. But what I noticed from my own behavior is that when having access to a low latency thread pool like that, I've started to use a very
Mariano
old
Acero
concept
just
in parallel
followed on
programming,
Twitch.
much
Mariano
more,
Acero
called the parallel
says,
for,
Hey, how are you?
which is very simple.
My headphones
All
are...
it does, it loops over a number of things, and it does them in parallel. That's all it does. And then it does, then it waits for all of them to finish before it proceeds. So all the measurements you saw in the previous slides were actually done in this way. It's just, it's not exactly this code, it's simplified a little bit, but you have this outer loop. First we prepare the graph coloring to compute these, what should be solved together. And then we make an outer for loop of 6 iterations. And for each iteration, we go through all the colors, and then we just solve all of them in parallel. Do that for all the colors. Then we solve these sequential batch only on the main thread. And then we do another parallel piece of work for the static contacts. And it's just very easy. It's very similar to the intuitive prototype version of this algorithm, right? And the only thing that I really needed to do to make this run efficiently was to set the thread pool in this elevated state. And I do that with a little scope variable. So when it enters that, it elevates the state. And if there's something to do on the main thread, it's also beneficial to do that when you enter the function. So in this case, I tell the workers to go to this elevated state, and then I know it's going to take 30, 40 microseconds for that before all the threads are ready and alert. So I have some time to do the graph coloring while waiting for that. And then you can just work with the worker threads, let the worker threads and the main thread work in a much more synchronized fashion. If you don't have to pay the price of this latency, that's proved, for me at least, to be a viable way to work with parallel programming. Saves a lot of boilerplate code. You don't have to allocate memory for these tasks. You don't have to copy the state. You don't have to come up with names for these tasks and all that tedious work that is not so pleasant. So for me, that has been quite eye-opening, or that's like a new way, that's sort of an old new way that's viable again. So conclusion, I think the takeaway here is not to do exactly what I did. I think the takeaway here should be that all these graphs we've looked at, having access to looking at the way the threads communicate in a visual way, I think for me has been very, very useful. And I don't think I would have come to these conclusions without seeing all these gaps in the timelines and how the threads collaborate.
Very
so
true.
I can highly recommend, if you're not visualizing your profiling data in that way, or collecting the profiling data that makes it possible, I would highly recommend doing that. And then depending on your workload, you may want to do something similar or something, or not do it, or something completely different. But then at least you're making an informed decision. Yeah, for me, changing the way synchronizing threads made a huge difference in performance. And that's the end of the talk. I just want to leave this with a little physics movie. And if you have any questions or you want to reach out, you can see my contact information down there. And thank you for listening.
There will be a chat afterwards. It's usually very interesting.
Thank you.
The audience in this conference seem to be mostly game developers.
So how many objects on the scene?
Could be around 10,000 maybe. I don't know. Maybe between 5 and 10,000 maybe.
So how do you think about the batch size in the parallel for? So you don't want to assign just a single constraint to as the unit of the task.
Yeah, it's a good question.
And then you have static versus dynamic scheduling.
Yeah, it's a good question. It's a little. You have to again measure.
The power saving is broken right now.
Batch size. I think it's 32 in my case.
A single frame takes less than half a millisecond now.
This got very specific very fast, but the number of tasks I generate, I think, is 4 times. Could be 6 times. I'm not entirely sure, but somewhere around that range. The number of workers, so I have a good number of tasks to choose from to not have so much static scheduling.
So
But also not too many, because too many tasks
for Dennis one more
is
time.
overhead.
Thank you. Is this still on? Okay. Okay.
So my first question is regarding the profiler you mentioned. You needed to build this from scratch, right? Is this your work that you had library that you actually could use? What was
this was my own custom profiler, yes. I have a history with profilers, so I like them, I use them a lot. But there is a really good free one called Tracy that you could use if you don't want to write your own. It's actually not that much work to write your own. You just have to be very careful how you measure performance, because you can't, if you want to measure
But it's very hard to beat Tracy.
performance of something lockless, you can't have a mutex in your profiler, because that can mess up the whole timeline.
In terms of UI,
so
it's just so
it
good.
has to be a lockless profiler also. But as long as you have that, collecting the data is really simple. You just record all the, I just call query performance counter and note the results, and then at the end of the frame, or when I visualize this, I kind of sort out all that and see which thing should go where, and so it doesn't affect the thing while measuring too much.
awesome? So I have a question. This was all CPU stuff,
Yes.
right? And everybody's crazy about GPUs in terms of rendering. So it doesn't
GPUs can do
sense
physics
to
as well.
offload some of that work during the physics, either the collision detection or the actual solving part, to GPU and use the resources.
You certainly can, and it has been done, but I'm not a big fan of the idea for 2 reasons, and one being that the GPU is pretty busy doing rendering. You probably want it to focus on that.
No.
Uh,
There is this, there is a little bit of misconception about multi-threadingness in games. It's that people often argue that it's worth to split game logic and input and rendering into multiple threads, because they can then kind of, you can have input processing for the current frame, which will then be affecting game state, which will then be rendered, and the input for the next frame can start right after you finish the input for your current frame. But this increases the latency, like just squeezing it as much. The only thing that matters is really the time from your input until it reaches the screen, and this is very serial. So if you can parallelize it by pushing it to GPU, it's not like GPU is doing anything in the meantime. If you forget about rendering multiple frames in parallel, which increases latency, then it's actually a great idea to do stuff in series on a GPU.
And the other one being the latency, or, well, if you want to put physics on the GPU, you either want very low latency and high bandwidth between the CPU and GPU and have them work in sync, so the CPU can say start crunching physics, or just the solver or whatever is on the GPU, and then get the result back. But it's going to be
not the result back.
Inefficient.
The trick is to keep the physics on the GPU. They should never leave the GPU.
Because the GPU is going to be busy rendering stuff, so it's not available just for random requests. Or you put all of it on the GPU and just tie it into the physics or the graphics.
Have you tried that?
No, because the result of the physics is also very tied to gameplay. So when you want the result of the physics on the CPU, and you want it usually immediately after you're done with it. And in our case, for Teardown, it's not really possible, because the physics could also result in things breaking, and you want to create new objects, and putting all of that on the GPU, you're going to end up with pretty much the whole game on the GPU, and that would be a nightmare.
Okay. I sometimes talk to game developers, and when we talk about physics, they are always complaining. And you spend your entire life on physics and physics engines. And my question is this the skill issue on the developer side? Or is this like inherently complex? How can a person get into physics and learn how to do it properly?
I think you just answered the first question with the second part. Like there aren't really a whole lot of good resources for learning physics. There used to be the bullet forums, but there's not that much activity these days. But like 10, 15 years ago, that was a very active forum where people helped each other, and we haven't seen much of that lately. So I don't know at this point. It's not particularly complicated compared to anything else in game development, I think. But it's it maybe doesn't have the same mass appeal as graphics. It would be hard to make like a shader toy for physics. I don't really know what that would look like. So getting people into it takes maybe a little bit more of an investment before it starts working. That could be one.
Right. So from your talk, we started with like mutex and synchronizing threads, and then we ended up on the spinning lockless implementation. Does this implementation have some sort of downsides? Like, are there situations where it shouldn't go this way because it wouldn't work, or is it just always better?
Well, the most obvious downside is that it can consume more power. It will require more energy, but I think that is only true in some situations, given how much.
I often become desensitized into how much power rendering uses, and This is the reason for this power save. Like, we have this power save feature in Automat. But whenever I run it on a laptop, it's really important. If it's terrible if a utility app just drains your battery so fast. So I care about power usage because low power usage also means the app is nicer to use. The laptop doesn't get hot when it runs it.
Shorter time the solver runs, I'm not convinced that the total amount of power would actually be less if it went to sleep and woke up like 100 times instead. But spinning on atomics like this is not something that is generally recommended. If you look at the whole system, like if you're running the game and a lot of other things, that will probably not work very well because the game is going to, if you get like a context switch in the middle of the solver while a lot of threads are waiting, spinning, then they're going to keep spinning until, if we say for some reason the main thread would be swapped out while the workers are spinning, waiting for more work, they will spin a whole time slice before the main thread gets swapped back in. I think in practice, though, I don't really see how or why that would happen. But if you run a lot of things on the machine, it's going to start to become really inefficient.
All right. I think we have time for one question from the
Yeah.
audience.
For games, this is spinning strategy. It's actually acceptable for games. They have to squeeze whatever they can out of performance, and it's kind of expected that they're going to use a lot of energy. With our frame time now, we are not very good still. System point. That should be steady.
Okay time.
Okay time?
When we need to go.
All right. So let's open up the floor for questions from the audience. Who would like to ask the question? Yes?
So this is more of a general physics programming question. So if you're applying the solver to multiple bodies, I would imagine that you start at a different point in the chain when you're applying impulses that it could potentially lead to a slightly different solution, right? Like it's order dependent. So what kind of general conventions are there for deciding what order to start in? Because I would imagine those would lead to slightly different results.
Yeah, that's entirely correct. That's also one of the reasons we want to have determinism. It's not only for networking purposes or anything, it's because of stability. If we solve the constraints in the same order every time, we're going to have a result that is slowly converging to the correct solution. Whereas if we solve them in random order every time, we're going to we're going to end up with disturbances that it can't compensate for appropriately. So we're going to end up with jittering. And there's also, I don't know if that was the question you were asking, there's also been, in the past, there's been experimentation with reordering constraints. Say you have a stack of objects, if you want to solve it from bottom to top order and things like that in order to increase stability for stacking. That's also been done. But I would say that that's a minor thing compared to the general stability.
If I could just clarify the question. The question was like, what kind of conventions are there for deciding what order to go in? If that makes sense. Like, is there particular conventions that for deciding what order to actually use?
Yeah, apart from these, if for stacking, for instance, if you want to solve from top to bottom, that's generally preferable. But I would say in practice, what I do and what I know other physics programmers also do is that there's some kind of consensus that it doesn't matter that much which order you solve it, as long as it's consistent. So what I do, I just do a radix sort. So I sort them per body, and it's incredibly fast. And I do it actually on the main thread before the solver starts. But it's at least with 32 threads, it doesn't really take up that much time on the profiler.
All right. Next question.
You mentioned there was potentially some sort of penalty from the operating system if you don't go to sleep. Is that a particular thing on particular operating systems?
It's just something I observed on Windows. I don't know if it's under some certain cases or if it's always. But if I make an error so that they're always spinning, I noticed that the operating system, I don't know if the punishment is intentional because this process is doing something bad, or if it is just the time slicing that makes it get swapped out more often in the middle of something. It could be either of those, I guess.
John?
Did you ever experiment with work stealing? Because you only have one work here, right?
Yeah. It's an excellent question. It's actually one I should have put on a slide for future work, because work stealing is generally a better algorithm where you don't have just one single queue of tasks, but you have one task queue per worker, and then they steal work from each other in the case they run out. So you have like a static batching that turns into dynamic batching once all the work is done, so to speak. And I want to try it. I haven't tried it yet. I also noticed in the profiler that these black gaps in between jobs with a lockless are so small that the potential speed up is pretty small, I think, in my case at least.
Holger?
Do you think that there is a way to overlap these iterations? Because you will be touching stuff that's not going to change during the previous iteration?
If that was the case, they would have ended up in the previous color.
You know, like the iterations, like when you're done with some of the...
Oh, I see. Potentially, there might be some opportunity for optimization in the overlap going from one iteration to the next, but it would... My intuition is that would be pretty small, but it's a good idea. Should maybe look into it.
Sam?
Yes. So I wonder, you described that on the main thread, you do things that I presume touch all n of the contact points, it sounded like. So is it, I'm trying to get an idea for how much more expensive the solve, each constraint solve is compared to just iterating like, because you, for example, said you sort them, right?
Right. Are you talking about a memory? Just
why is it expensive? Why can you go over all n contact points on the main thread that you can't solve? Like, how much more expensive?
Yeah, it's a lot of computations to solve each constraint, so that there's a significant amount of operations that needs to be carried out. So it's, yeah. But you're right that going over and touching the memory on the main thread for everyone, that could, if you have a lot of constraints, that could potentially be a bit expensive. The total memory for all the constraints, even if you have 10,000, they're still all going to fit, maybe not in the L2 cache, but at least in the L3 cache. So it's not going to be a major bottleneck when it comes to memory.
And just a quick follow-up then. Mm-hmm. Are there variations in how complex a solver could be? Like, for example, is teardown solver a lot more complicated than what somebody else might do? Or
I don't think so. They usually, the solvers, at least from what I know, are relatively similar as long as they follow this projected Gauss-Seidel or sequential impulse. They could be implemented a little differently. The new one that we saw here is actually a bit different from the one in teardown on in a number of ways. But it's the differences are rather small, I think.
Brian?
So I'm not a good physics programmer, so let me know if this doesn't make any sense. But with the sequence of iterations, you have, like, let's just say you have blue color, red color, green color, and then the second iteration you do blue, green, red, whatever the order is. You do that many subsequent times. Is there a dependency between, like, blue number 2 and red number 1, if that makes sense? So, like, could you do all the blues first and all the reds and all the greens, or can you not slice it that way?
No, you have to solve all the colors in one iteration before you can start the next one. It's almost like the iteration is just a continuation of this sequential thing. So you have to finish all of them before you can start the next one.
The iteration is just basically just to make the step small enough so that you have fine enough correction, right? That's the only reason we do iteration.
The reason there are iterations in the solver is to increase accuracy, because it converges towards the solution. The more iterations we take, the closer we get to the solution.
And how did it happen that it's exactly 6? How did you
it's just experimentation, like what you need for the game.
Okay. Will this be stable from game to game, or?
From what I know, most games use 4 or 8. There are probably some games using a bit more, some a bit less. Some physics engines let you set that per body. So if you have a simulation island with all low iteration count, then it's not going to spend so much resources simulating that island. So it can look a little different, but it's a performance quality trade-off.
All right, Taha?
Yeah, so I have a question. This is a more general physics engine optimization, and that's, do you do a thing that, for example, you measure, for example, you see if an object is really far from the player camera, you do less physics iterations on it? Or if you see that the object is really stressing the physics engine, you just like
it's a nice idea.
Try to do less iterations on it?
Usually, no. I don't do that, at least. I don't know if someone else is doing it. I think it's pretty uncommon, because generally, if you have things that are scrambling around somewhere trying to settle, if you turn down the iteration count, the simulation quality is going to go down, which means they're going to be more shaky and jittery, which it's going to keep them alive for a longer time. So when something settles, you can take them out of the simulation. So at a larger scale, you might actually waste time by doing that.
Are there SQ?
Have you thought about keep storing in the objects if they are solved, so that you say the first color is one value, the second, and then you can check, hey, I'm in the second wave, have both of these contacts been solved in the previous, and therefore you don't have gaps where you have to sort of collect everything?
Do you mean for each iteration you would do this to see if they need further solving, or I'm not sure.
Yeah, so if you have a contact in the, what would you say, the second color, right? And that contact can only be solved when the first iteration is done. But it doesn't have, the whole first iteration doesn't have to be done. Only those two objects.
I see what you mean. Yeah, no, I have not experimented with that. I think that would be a very complicated thing to implement unless you want to do it, because then you want to have atomics for that checking. It's an interesting idea. I think it would be a lot of locking and quite expensive, but it could be worth checking.
All right.
Dumb question. If there are no good resources, when can we get your book?
I don't think I'm not planning on writing a book, but I agree that there should be more physics resources. There's been a couple of initiatives to do more. The best I know is Erin Cato's blog. It's very good, and also if you're interested in the solver specifically, he released just last year a project called Solver 2D. It's on the same GitHub account as Box2D. That is a simplified implementation of, 10, 11 different solvers. And the code is very easy to read. It's like written just to compare the solvers qualitatively. So it's not written for performance. And that's a good resource if you want to learn what different solvers do.
But besides Erin Cato's blog, there is also voxagon.se blog by Dennis himself. So while we wait for his book, you can go to this website, voxagon.se. It's Swedish domain, I presume. And Dennis has amazing blog posts, very detailed, very nicely written. You can go a lot, you can learn a lot from these blogs. So go check out voxagon.se.
Thank you. Thank you.
Masha.
Yeah, so you said that bad things would happen if you have more than 10 colors around like that. Is it the same as you did with sequences, with trial and error iterations? Or like there is some dependence on the number of objects, like how to determine the number of colors?
Yeah, the reason I want to keep the number of colors, I want to cap the number of colors is to not have, because each new color requires a full synchronization, so there's going to be some time lost. And if you don't have enough work in each color, it's just going to be waste at that point. So it's a little bit of trial and error to find that sweet spot. I think in my code, I actually have 16 as the cap, but it usually never reaches that. It's finished by the time it gets to 10, 11, 12. And then I have another cap at how, when there are only fewer than a certain number of constraints left, I just put them in this overflow sequential bin. And I think that number is maybe 32 or something that can be solved very efficiently in sequence. I just don't bother doing any labeling for. I just quickly want to proceed to the actual solver.
Thank you.
Yes.
How did using SIMD instructions factor into the optimization? For example, was this important, or was having enough frames?
It's a good question. If you go to Erin's blog, he's been experimenting with that. So he's actually doing graph coloring also for the purpose of SIMD. So he solves parallel on a bunch of different threads, and on each thread he solves constraints with graph coloring also on different lanes with SIMD, which is pretty cool. The new Box2D is amazingly fast.
All right. Thank you so much. This was so many questions. A round of applause. Dennis Gustafsson.
Thank you. Thank you.
Box2D is amazingly fast, but what's more impressive, it's amazingly stable. It's one of those few physics engines that they don't do silly things. It produces very smooth animations. simulations. I think I fixed the sleeping. Not super sure about this. I will have to read more about optimizing spikes, rendering spikes. I think there is an opportunity to do something here. We could probably make it a little bit nicer if we had access to some more GPU side information. And now that I started playing with those command buffers, Vulkan command buffers, maybe it's possible to use one of those extensions. Anyway, we'll do this next time. So for today, we won with the GPU. It renders actually on my laptop properly, and if this code is correct, also the power saving feature should be working as well. That should be here. Okay, so I guess this is it for today. See you on Friday. Bye bye.